Hello and welcome to episode 1 of Programming Applications and Programming Languages, where today we're going to be talking about the overview and evaluation of a programming language using a specific algorithm. Previously in the last episode we talked about that Swiss Army knife, where you can have a Swiss Army knife could be great for cutting a rope in a forest, but might be pretty useless at cutting down a tree. And then we can use that to talk about our levels of programming languages and programming domains. In this video we're going to be expanding on that, where we will be using, comparing the right kind of saw for the job kind of thing, where we will be able to look through our languages and very quickly be able to work out this one's easier to read, this one's easier to write, this one's better at memory management, and why. And we can do this with a TPK algorithm. So the TPK algorithm is a small benchmark program made in the 1970s, and it's there to help compare programming features, programming syntax, and the core jobs is it's there to help us evaluate readability, writability, reliability, and expressiveness. So, with that in mind, it's not here to help solve real-world problems. It's purely academic or educational. So the TPK algorithm will read 11 numbers from input, it will store them in an array, it will flip the array, or reverse the array, it applies the function the square root of the absolute value of the element, plus 5 times the element to the power of 3, and then for each one of these results, if the result is greater than 400, it will print too large, otherwise it will print out the computed value. So, why is this algorithm used if it's purely academic? Well, this algorithm implements arrays, inputs, reversing loops, functions, conditions, mathematical computations, and outputs, which might just sound like a list of randomly chosen items, but they're actually like the core principles or the core building blocks needed to be able to implement any other feature. If you want lambdas or some other form of highly complicated, slightly high-level feature, you can implement that self as long as you've got these core elements. So that's why we use these core elements. And because the logic or the steps are the same for every programming language, because we're following the same algorithm, it's quite easy to compare your syntax, how you define functions, how you handle types and errors, how expressive it is, and how readable it is. Because they should be side to side. I have my C code here and my Python code here. It's like, that's how I define an array, that's how I take an input, that's how I do my matching, that's etc, etc, etc. So it's slightly more realistic than Hello World. It's still an educational thing, but you should be able to understand it better than just having print Hello World in 5 languages and it all looks the same. So it's a small little algorithm which makes it slightly more manageable than trying to compare realistic real-world applications, because there are hundreds of pages of code instead of these 15 lines. So the first thing we want to talk about is expressiveness. Expressiveness refers to the way that a programming language can implement natural and consistent requirements. So it should be highly expressive, which means I should be able to read it and naturally understand what it does. So for iterating through an array, I should be able to have a for loop, which can count up or down, where I can say for item in length of list, and it will just loop through length of list. While a low expressive language would be having to manually do pointer manipulation to increase my way up the stack and not quite knowing where anything is. Well, or having to keep track of where everything is manually, having to keep track of the upper bounds, the lower bounds, just to make sure things don't crash or hit a Stack Overflow, etc, etc. An expressive math syntax follows standard notation, so this is square root, SQRT, or abs for absolute, things like this. These are mathematical syntaxes which have been standardized in textbooks, Wikipedia, your general maths classes. I should be able to find the same definitions almost anywhere when I'm following or re-implementing a formula from an internet or from a textbook. So I should just be able to call these. A low expressive thing would be some form of complex math call to an API or to some low-level system using assembly, or having to implement it myself, where I can't just say SQRT and call in a square root function. I having to do some form of power to 0.5 to do that, or some other complex system that doesn't follow a standard notation. Array handling, basically, so let's say it's either a 0 or 1 based array, which means it starts at first item's element 0 or the first item's element 1, and then I should just be able to increase that number and move along my array. So element 2 would be the next item, element 3, so on and so forth. Why a low expressive array handling would be having to do manual memory management, having to keep track of local pointers, where the bounds are, where does my array start, where does it end, and it not just telling me when I get to my array or the end of it. If I increase it again, it will just print out random memory. That's not expressive. Why, if it tells me no, you're out of bounds, that would be an expressive expressive use of array handling. And then error handling. We want clear checks. We want to be able to do if this then, or if that's then. We don't want to have to do any form of here's a sum, so to work out if we've hit the bottom of our values, we're going to subtract two numbers, and if it's greater than 0, we want to branch off to this statement, or if it's less than 0, we want to go to this statement. That's not expressive. Simple expressive was if this then, or in Haskell it's like guard something otherwise. Clearly defined conditions. Orthogonality, or consistency, is a very easy principle, but it sounds quite scary. And we want to say that our programming language has a small amount of constraints. So there's a few set of rules that we have to follow. And these constraints can be joined together freely. So my arrays can't be longer than X amount, but I can also then loop through these, and I can't loop past a limit. So a small set of constructs or conditions that can freely be joined together, and these combinations have a purpose. There is a reason we want to do this. So a bad example of consistency is arrays can't be returned in C, but pointers can be. So I have to define my array somewhere else, create a function, and then have to return the pointers to each element of said array. That's hard to follow. It's fairly strict rules. Why, with something like Python, I could return turn an array straight away. So fewer exceptions means the language is easier to read and write and learn. And generally it's seen as slightly more reliable because there fewer bugs should occur. This isn't because of the fewer rules having fewer bugs. It's having an easier to learn and easier to write language should lead to fewer bugs. Now, readability and writability. Readability is the ease that a human can understand the code, logic and flow of an existing code base, or a code base you haven't looked at before, you haven't worked with before. In theory, something you probably haven't dealt with. This does assume that you do already know the programming language, but you should be able to just take a glance at certain lines without it and understand what's happening there. So that means clear and meaningful syntax, clear keywords, good consistent rules, and a good use of data types. So for people who move to C and from languages like Python who doesn't know that 1's true and 0 is false because Boolean doesn't exist natively, so a good use of data types would be having booleans or a null value or things like that. So that would be good readability. Writability is how easy a person can start creating a solution for a specific problem or a specific task, and how easy it can be that they can finish it. So expressive syntax is quite an important one. Syntax which is easy to learn and memorize and just write without having to refer back to documentation. Abstraction, so you can use functions and classes quite easily off the bat without having to use weird branch statements to jump around. And fairly flexible rules, which is again rather one of the reasons why Python has taken off so much in education. And then the next one is, so here are some examples of writability, of just implementing the function the absolute value of x plus 5 to the power 5 of the element to the power of 3. I don't know why the power's gone from the formula in that version, but oh well. On the left is C, as you can see it's quite long. Y on the right is Python, and it's quite easy to implement. So we're doing our checks and implementing our function all in one there with Python and C. You can see with C version we will have to actually call in other functions, while in Python they're built in. Then we've got reliability and cost. Reliability is how consistently a program can perform its intended function or feature without failure or crashing under special conditions. So extremely large numbers, extreme values, things like that. So there are a couple of ways we can make things fairly reliable, which is type checking. So if a function requires a number, we always make sure we pass it a number. Some languages will let you pass anything, JavaScript, into a function, and it will try and deal with it. But I don't want to be multiplying my strings or subtracting from my strings. So checking that the intended input is always there. Don't just accept any data type. Expressive handling. If a value is too big, we would like a graceful way to exit that function without crashing. So like returning an error that value is too big. Things like that. Memory safe. Having restricting the ways we can access memory. We shouldn't be allowed to directly access hardware if we don't understand it. So having some form of buffers, something like that. This prevents us corrupting index arrays, corrupting array indices, and making sure that we don't use up other parts of memory which haven't been assigned to our program. So something, small little comparison is C is quite a really powerful program, and it's really good for things which are low level, and it lets you directly access all of the hardware and maths of your computer. But because of this, it lets us do point arithmetic, which, if you don't know what you're doing, can lead to mistakes with memory that can lead to a system crashing. Why things like Java and Rust have very strict bounds on memory and to handle the memory management for you, so they might be slightly more reliable, so it's harder for you to make a mistake that could break your computer. And then cost. So cost is a very subjective thing, and we're not talking about pure money here. Sometimes we can talk about efficiency, future maintainability, development times, and things like that. So one of the ways we will consider cost is learnability. How long will it take the programmer to learn the syntax and libraries needed to create said product? Writability, that one's pretty obvious. It's how much time and effort will it take to be able to turn the algorithm into actual functioning code. Readability is how easy can a person read through it who hasn't touched it before. This also includes debugging time, and then time for someone else to take over the project. And then execution efficiency. How long will our program require, taking up CPU and RAM time? Can this time be saved somehow? It's like high-level programming languages like Python are often slower. While they're faster to write, they're slower to run, which is more time on your system that could be assigned to other tasks. And then lexical elements. So one of the other things is it helps us compare what built-in lexical elements they are. Lexical elements are the very smallest building blocks of a programming language. These are the individual tokens which can be used. So this would be keywords. So if is a lexicon element, while, return, and then all of our operators are. So plus, minus, the logical and, logical or. And then we've got identity, so names, functions, classes, variables, and then just the literal pieces of data, so strings, booleans, and numbers. So good lexical design is there to help maximize readability and writability. So we've got ourselves a little table to help understand good lexical design. So with consistency, symbols should have a constant meaning across all contexts. An add should only be an add, but an add should be able to both add both types of numbers or concatenate strings. It should always be clear what a symbol does. And then distinctiveness, symbols should always look visually different depending on their task. So equals for assignment and double equals for checking if something is output to there, for logical equals. They should be clear that they're different, which is why we use the double equals and the single equals. We shouldn't be using one symbol for both, as it's not distinct. And then keywords should match the natural language equivalent, so the human language and the human thought version. So repeat until is quite often seen as more descriptive than do while. So we want it to be very upfront. We can look at keyword and bam, that's what it does. That's what in my mind I think it does, and that's what it actually does. So now we're going to look through a few little languages. So this is Fortran. So it's very mathematical. It uses do loops and labels, and it's designed for scientific computing, and it's not overly friendly for beginners. So as you can see, at the very top, we've defined our function. We've then created a dimension. A dimension is the same as an array in Fortran. We're then loading our array. We are doing our inputs, which is a little loop here. We're going through our loop and we're recalling the function, and then we're checking if y is greater than 400, and for greater than we use gt, and if it is greater than 400, we are printing too large to the terminal. Otherwise we're printing out y being the function that we've defined 3 lines up, and then we are doing this 10 times, as you see, 10 continue. C is a lot more readable. It's got clearly defined functions and loops. It's got explicit types, so you can see what's a double, you can see what's an integer, you can see clear memory handling, so you can... Yeah, well, there you go. You can see 2 lines down from the main loop. I don't know why I was pointing at it, you can't see. Double A11 is our array, and we're giving it the value. The values that we're applying to everything will be our formula. And then we are doing our first loop, which is scanf, which is taking in user inputs from the terminal. That's still not overly clear, it's not overly readable, but you can quite clearly work out what's a loop and for how many times it's doing it, because the amount of loops we're doing is clearly defined in the opening brackets. So we're starting at 0, we're going to less than 10, less than or equal to 10, and we're increasing by 1 every time. And then we're doing our second loop, which is applying our formula to every item in our array, and then we are evaluating each item to see if it's too large or not. And then we have Python, which is quite a small, quite clear thing. We are defining our function again, we are creating ourselves an array, and we're doing this of 11 inputs, and we can do that within our array declaration. We are then looping through our loop to check if it is too large or too small, and we're doing this backwards. So we're doing it from -1 up to 10, and we're taking steps of negative. Basically, we're going backwards. So it's quite an expressive, quite clear to read language. So all of these languages have their own pros and cons. And when you start working in industry, you'll realize, actually, there is a reason I have to use C. But if you're just for an academic purpose trying to compare readability, writability, maintainability, we would implement the TPK algorithm. So I hope you learned something, I hope this makes sense, and I will see you again soon.